All right. Really should have just kept going with this, but this is the last page here, so we'll keep going with the flux and changing area. I did this one separate. I guess another good reason to do this one separate is because this is a little bit more focused on the idea of flux. Again, flux is field. Those are those X's there, and it's not. Don't worry about counting the number of X's. You can kind of count the X's, but there was a picture on one of the other homeworks or something that someone started counting X's, and they're like, well, that if you just had it slightly over, it would be 2 versus 1. It doesn't matter where it is inside, where that block is. If it's inside, that is one rectangle worth of field. So think of the X's as like a constant shading area rather than like number of X's. It's more of a shade. Anyway, it's how much of the field area you capture with that area. So the field is the shaded area or the Xed area times the amount of area that you're capturing. That's flux. But remember, change in flux is the change in field or area. And usually it's the area changing there. And that is what creates that change in flux is what leads to a voltage. All right. All right. So let's look at what's going on. In each case, they're all moving at the same velocity. So rank the magnitude of the induced voltage. Again, which one is changing the flux the most? Well, since we're not varying the field, it's all about area. Which one's changing the area captured the quickest? So A has a very large height, which we call L, right? And versus B, C, and D. So A is going to capture the most area or change its area the fastest, and thus will have the largest voltage. A, most area change. Some of you were just saying the largest L, right? If you thought about EMF equaling B times L times V, the velocity, those are the different factors that can affect the EMF, the field, the height of it, and the velocity. That's on your equation sheet as well, but I like to think of it as the area as well. So A is the most area change or the biggest L. Again, B, C, and D are all the same rectangle. They're all the same L. So now it's all about how much area you're getting. Well, B is moving inwards, whereas D is moving out. So they're going to be opposite direction currents, right? B will go kind of around this way for I maybe, whereas D, it's going to reverse and the I is going to go the other way. But they will be the same amount because it's the same changing area with the same velocity and the same L and the same area there. Key, though, is that it does reverse direction of the current as it goes in versus going out. You're getting more area versus you're getting less area, going up, going down. But the change is the same. And then finally, C is the least because it's all in the field. You're not changing the flux at all. You're not gaining or losing area. You've trapped a full rectangle of field, you move over a little bit, you still have the same amount of flux. That's not changing, and so you don't induce the voltage. So A is the most area, B and C, excuse me, B and D changing, we'll say in versus out. And finally, C, no changing flux. All right. And so that's the key with that one. All right. And then lastly, the difference between motors and generators. Big idea, motors, electricity, and magnetism, or excuse me, electricity in through magnetism, you get motion, kinetic energy. Generator, you get kinetic energy or motion in, and through magnetism, you get electricity. So just the opposite of it. In fact, the same device can do both things. So electrical device that converts kinetic energy into electrical energy. That's that motion into electricity, and then thermal too, because you're always going to get some heat. That is the generator. All right. Electrical device that converts electrical energy into kinetic energy. So we're going from electricity into motion. That's an electric motor. What's not an example of a power plant that uses a generator? At least an induction generator, would be a fuel cell. Right? Hydroelectric is going to use water. Nuclear and gas are both using steam. Both of those things are moving, and they spin a coil inside of a magnetic field, and that produces the electricity. Physics concept behind the electrical motor is, all right, so this one's a little tricky. Behind the motor is a force on a wire, but there's also an electromagnetic component to it. You're running electricity through that wire, which is usually in a coil, producing your own little electromagnet there. So it's kind of both. I think it's primarily force on a wire, but it is also electromagnetism. You might even say it's ferromagnetism because there are probably some permanent magnets in that electric motor, but let's not get too involved there. It's definitely not induction. All right, and then the physics concept behind electric generator, once again, it could be a little bit of ferromagnetism if you have a permanent magnet in it, but that's not the concept that's going on there. Electromagnetism, usually not using electromagnets in a generator. It's kind of the opposite of that. You don't want to use electricity in your thing you're trying to make electricity with. Think about that for a second. All right, that's a little weird. It works better if you have some sort of strong permanent magnet and then you move that motion through it and you capture that force with induction in what would be an electromagnet if you ran electricity through it the opposite way. So it's kind of electromagnetism, but it's the induction. Now, it's got the word electromagnetic in it, electromagnetic induction. Yeah, and that is the unit. Again, not any math, very, very little math. You still get the triples and whatnot like that. A lot of conceptual stuff on the 5 topics. So study hard, ask questions, see all of us for extra help if you need it. We're here to make sure you learn it as best you can and do the best that you can. So we will see you all. I say we because I think I'm passing these videos out, but I will definitely see all of you in class tomorrow. Today, I don't know when you're watching this.